Okay. So in a transmission line protection, okay, of course, transmission line is the most fault-prone area of power system because it is overhead. It is exposed to the atmosphere environment. So we have a lot of protections in transmission line. I'm just listing the various protections in a very brief manner. First of all and foremost of all is the distance protection. Then comes the other part of the distance. I mean, distance is the primary protection. Along with distance protection, the important protection also that comes, it is not the other protection, it is the carrier aided protection, carrier aided tripping. The other 20% of that primary protection zone of distance protection, that is protected by that second, this one 85, that is carrier aided tripping. You have a lot of carrier schemes over here. Okay, now there is another type of protection which is probably the best protection in this whole world, that is line differential protection for line protection. But it is used typically for short lines up to 10 maybe 10-12 kilometer, where distance protection is generally unable to discriminate that zones properly, because in a very short line the impedance variation between a 80% fault and a 100% fault is very low, and distance protection is not able to properly discriminate that. That is why line differential is the most used protection in the shorter version of this line. Then we have a backup of distance protection, the directional overcurrent and the directional arc fault protection, 67 and 67N. In the higher voltage, typically 220 kV and up, we have over voltage protection because we do not want our equipment to connected equipment to be subjected to over voltages. We have power swing, block and trip. Trip is not very much used in many places in India. Typically, the utilities don't use power swing trip, but power swing block is a very much used protection. During swings, the distance zones tend to operate indiscriminately, so we need to understand power swings and block the distance zone during that time so that no nuisance tripping takes place. We also have a switch on to fault or trip on reclose protection, which deals with closing a line onto fault. There our actually memory voltage and those things are not available. Probably the voltage will not rise fast enough for the zone 1 or zone 2 protection to operate. So we have a separate protection which is applicable only during closing. Some additional control and supervision functions which are built in the transmission line protection relays are fuse cell supervision. If the VT fuse cell goes out, then the distance protection will not occur because it doesn't have voltage. But the line is healthy, there's no fault in the line. It might trip the line. Under those conditions, we have this fuse cell supervision, which is again used for blocking of distance protection. And there is a totally separate area which is auto reclose and synchronism check, which is not a protection, it is an ancillary function. So we'll be having separate sessions on that. Then I'll have to click. Okay. Now I have divided this protection into 5 modules. Chandan told 4 because he had the details of only 4. Module 1 is what we are doing today. The theoretical concepts of this distance protection, all those reach and how to calculate reach and those things. Module 2 will be totally upon communication aided schemes and line backup protection, directional overcurrent at fault, case studies on that, mainly this carrier protection. Module 3 will be all the other things in line protection, power swing block, SOTF, broken conductor, VT fuse cell, stop bus, over voltage, and some complicated setting example. This complicated setting example was to be taken over here only, but since we are not doing directional overcurrent at fault, I have kept it a bit later. Module 4 will be fully on auto reclose. The whole 2-hour session on auto reclose, various timers, settings, concepts, wiring diagrams, and all those things. As far as what I have seen in my utility, that much only I'll be able to share. Module 5, this I have not yet prepared. I'll need a little bit time, but that will be purely on mutual coupling in parallel lines, which is a quite a little complicated concept because this is a series kind of a fault. This is not a shunt fault, which you are very much not a fault basically. The mutual coupling actually changes operates in a series mode in the line. The voltages induced and all those things are in a series, so that complicates matters a bit. We are more used to the shunt kind of faults. So this will be another part, mutual coupling in parallel lines, concepts, various configurations, susceptible configurations, where mutual coupling have to be wary about, where it can go wrong, the theoretical calculations of maximum and minimum overreach, underreach, all those things, and some real life examples of relay misoperation. Okay. Now this is just prepared a little bit of a content. Now I'm coming to the principle of operation. Okay, I think the main course. So distance protection, principle of operation. The principle of operation is the impedance of any transmission line or feeder or any conductor is proportional to its length. That we all know. Obviously, as the length increases, the impedance increases. Now, in a radially, okay, all these equations I have written over here are all applicable only for a radial line. Distance protection works एकदम perfect in a radial line. Wherever there is infeed, there is some source of errors. We'll talk about them later. In a radial line, what happens if there is a fault over here? The impedance seen by this relay, the voltage divided by the current seen by this 21 relay, is proportional to the distance of the fault from the relaying location. This particular fact can be used to calibrate the relay to respond to a fault at various distances away from the relaying location. What happens in overcurrent is, whenever overcurrent, it's very difficult to restrict zones, where distance protection is very easy to restrict the zones. Since my conductor length is known, my conductor impedance is known, I can easily have a protection so that suppose 1 to 100 kilometer you operate in 1 to 100 kilometer fault you operate in 0 millisecond. 100 to 200 kilometer you operate in this millisecond. 300 to 500 kilometer you operate in this millisecond. Like that I can calibrate distance protection. Of course, it is not that easy to do it in the practical life, but the theoretical concept is that. Okay, now just let me go through this. This one I read out. So if we have a relay which corresponds to V by I at the relaying point, we can calibrate the relay to respond to a fault at various distances away from the relaying location. Now what happens in a fault is, in the event of a fault, certain changes occur in the measured voltage and current, causing a variation in the measured impedance. This measured impedance is the vital one, is compared against set values, calibrated values within the relay and the tripping decision taken. What I was saying, 0 to 100, 0 milliseconds, kilometers. Okay, relay is seeing in terms of impedance, but the event will happen in terms of kilometers. So this helps us in creating a time coordinated primary and backup protection schemes. Let's go to the next. Okay, zones of protection. Distance protection is all about protection zones. Zone 1, Zone 2, Zone 3, Zone 4 and higher zones. We have all heard about it. They are classified on the basis of distance from relaying point. You have the relaying point at the origin. You have buses, suppose bus F, bus G, bus H, bus I. You can start with this diagram. I have a zone 1. We are all talking about this particular relay, only this particular relay, where I am putting my pointer on. The zone 1 from this relay will be having something, let's say it is a 100 kilometer, 100 kilometer, 100 kilometer line. Let us suppose. We are having 0 to 80 kilometer will be zone 1 for this line. Maybe. We have written 0 to 80% zone 1 of line length. So this portion, any fault occurs, it will trip in 0 millisecond. If the fault occurs within zone 2, Z2 F is this bus, so Z2F is the zone 2 reach of this particular relay. Let's say it is some 120% of the line. So any fault occurs between 0 to 120%, it will trip in, let's say, T2 time, which is higher than T1. T2 is higher than T1. And similarly for zone 3. So it will trip in a more higher time. So what is happening? I have a section where I have instantaneous tripping. I have a section which have an intermediate delay. I have a section which have a higher delay. Now similarly, this fellow, this G bus will also have a relay which has its own zone 1, and zone 2, and zone 3. So what will happen? The nearest area of the fault, when the fault occurs between this section, only this relay will trip, the back relays won't trip. Suppose a fault occurs in this section. It will come in the zone 1 of this relay, but not in the zone 1 of this relay. This relay will see it in zone 2. So if this relay fails to clear the fault, only then this relay will come into operation. So like this, we can have a very clear-cut discrimination in the fault. What we have known about faults is what? You have to clear it fast, you have to be selective. Speed, selectivity, reliability. These are 3 pillars of protection. Speed is fast, selectivity is most vital. All our meetings and all mail shipping takes place because protection is not operating selectivity. Is losing selectivity somewhere where it should not operate, it operates. These things happen. So distance protection is a very useful method of very easy and useful method of having a selective protection. Now this one is self-explanatory. Operating time will be progressive. T1, T2, T3 is the timings of the zone 1, zone 2, zone 3. With the zone 3 tipping time being more than the zone 2 tipping time being more than the zone 1 tipping time. It is inherently directional. Now reverse zone can also be independently progressive. You can see like the method we are having a progressive zone over here in the forward direction. We can also have a progressive zone in the backward direction. It is so flexible. Generally we use only one zone for backward protection, but we can have. Okay, now we come to the key advantages of distance protection. The first line is very important. The fault coverage of the protected circuit is virtually independent of source impedance variation. Probably this is the most important benefit that we get out of distance protection. Matlab kya? Means suppose in a network we have 5 generators. Tomorrow we have 10 generators. The fault current will change, but in general the distance protection parameter unless the network changes. Network means in the front of the relaying point. Till that point of time, there will be no change, normally no change in the distance protection parameters. So every time some generator is out of service, every time some generator is in service, every time the fault level changes, we don't need to change our distance protection setting, because unless the parameters related to impedance changes in front of the relay, means there is a new line being added, new substation coming up, or the conductor is being changed, or the city ratio and all those things being changed. Otherwise, we don't need to have any change in the protection settings. In overcurrent, what happens? When the fault level behind the relay location increases, then the time of the operation decreases. So we have a little bit difficulty. Network parameter change affects overcurrent and hot fault very much. But distance protection is not affected by source impedance variation, means fault level variation. No communication needed. That is why it is low cost. Line differential is of course the best form of protection. We all know it. Those who are a bit old to protection, everybody knows line differential is the best. Because there's no falsifying things in the line differential. But the problem with line differential is high cost is involved, because the remote end current parameters has to come to the local end. Then only the differential protection can be activated. That creates a high cost. That involves a high cost. So no communication needed. Only local voltage and current is necessary for the distance protection to operate. This one I have already discussed. Area and zone selective tripping at minimal cost. Along with protect communication intertrip schemes, matlab that area schemes, PUTT, POTT, blocking, it creates a unit protection scheme. Unit protection scheme means zone specific protection. This bus to this bus A to bus B, only for faults within bus A to bus B or within the transmission line section. This distance protection along with communication intertrip will respond. So that is, in this form, it is eminently suitable for application with high speed auto reclose. What do we need in an auto reclose? In an auto reclose, we need the fault has to be in the line section. If the fault is outside the line section and we reclose, then we are not doing the right thing. We are creating problems. It is in other section. So along with this communication interface, this unit protection, this thing happening, it will respond to only faults within my line section. I am very sure of it. I am 100% sure of it. There, this auto reclose can be very usefully incorporated. So therein also distance protection helps. This is another advantage. We don't, the people who are new into protection will not feel this one. People who are old will feel it better. The characteristic of a distance protection may be plotted on an RX diagram very easily. Thus, loci of power system impedances as seen by the relay during faults, power swing, load fluctuation can be seen on the same diagram, and relay performance during all these system abnormalities will be studied very easily. We have different kinds of power system happening. Power system impedance fluctuates from the relaying location for different reasons, for faults, for power swing, for load fluctuation, for generator load and roasting changes, generator loss of field, foul slip, and all those things. All that happenings can be plotted on a single diagram. That is a very essential, investigation tool for the protection engineer. So we can, distance protection help in this. In other forms of protection, it is not, it is a very individualistic protection, but in distance protection, the line protection, generator protection, and maybe transformer protection can be plotted in the same RX plane. So that is useful. If I am not able to explain this one, probably in the later slides you will get the idea what I am trying to say. Facility of obtaining accurate fault location. Ultimately, for the operation people and the line patrolling people, it is kahan pe fault hua. That is the most important thing for them. So distance protection gives a quite an accurate fault location. Single-ended fault location is accurate in most cases. Of course, single-ended means only from the local voltage and current. Double-ended fault location is more accurate, where you have the remote end voltage and current also coming into the relay. But in India, it's at least in my utility, I have seen only mainly single-ended fault location. Okay, now this is a diagram of the CTPD connection. I have just included it just to clarify one or the other thing. That everything will happen if the CTPD connections are correct. If the CTPD connection agar ulat jata hai, then distance protection will see faults in the reverse mode. Matlab then instead of line protection, it will become a bus bar protection. Okay, so the CT polarity has to be towards the line side. Sometimes it goes wrong in our utility also. Sometimes it has happened. CT was shorted on the bus side, and during remote, other end faults it was tripping, reverse faults it was tripping. So this is one important area. The CT shorting should be on the equipment side, means on the protected equipment side. And the other part is the relay where it enters. The CT phase side where it enters should be defined as a phase terminal of the relay, and the CT shorting should enter the neutral terminal of the relay. Although this is a mutual line compensation is also there in this particular drawing, I am not going into it. But this CT ultimately should come back over here. So that there are two polarities. One over in the CT hardware itself, the secondary junction box or the JB, and the relay. Relay may be, it is mentioned which is the entering side and which is the outgoing side. So only current entering through C3 and C2 will be taken as current at angle 0. If the current enters through C2 and goes out through C3, it will be taken as 180-degree current with respect to the voltage. Similarly, voltages also have the polarity as shown in the next slide. Voltages also have the neutral side of the secondary, PT secondary should go to the neutral of the relay, and the phase sides of the PT secondary, just as shown over here, should go to the phase side of the relay. These connections have to be okay for the distance protection to work correctly. Now, if it is set properly, then we have the VI plane to RX plane conversion. What is this conversion? We are familiar with the VI plane. Normally what happens? In an inductive system, current lags voltage by some 60, 70, 90 degree line angle maybe. It lags. So this is our majority fault scenario, the quadrant 1 that we call. Okay, now this quadrant in VI plane, the fourth quadrant or the conventional fourth quadrant of VI plane is the first quadrant of RX plane. This is the impedance plane, RX plane. So this quadrant is mapped over here. This quadrant where the I lags voltage from 91 to 180 degree is mapped as the second quadrant of the Z plane. Means the VI plane, if the rotation is in a clockwise direction, that will be anti-clockwise in the Z plane, in the impedance plane. Okay, so this is important. So in an overcurrent relay, what used to happen? When I'll talk about overcurrent relay in the next webinar, then we'll see that this is the operating region of my overcurrent relay. Voltage reference current will be lagging in the inductive systems. I'm not talking about series compensated lines, normal inductive lines that we see in our day-to-day life mostly. Okay, so this is the operating region. Now this same operating region is mapped in the RX plane as this region. So rest of the things I'm not going into detail. These are all inductive fault current, X is positive, capacitive fault current, X is negative. Okay, so we all have inductive fault current. So this is our operating region. Most of our distance relay operations takes place in quadrant number 1. Means in VI the quadrant number 4, conventional quadrant number 4. Okay, let me move further. There are two effects that you need to understand. We talk about it very much. The words confuse us a little bit. So it is underreach and overreach. So what is underreach and what is overreach? Let us understand with a little bit somewhat example. Okay, let me read once more. Fault current contribution from remote bus make the relay measure higher apparent impedance. So what is happening? Suppose I have a relay. Now we are coming into the distance relay errors. This overreach and underreach are the errors of distance relay. We are having what will this distance relay measure? This distance relay will measure the voltage at this point and the current at this point. But if the fault appears, suppose beyond this bus, so there will be Infeed from this line, this source there will be Infeed. There are obviously fault sources on the remote bus also. They will be feeding this fault. So what will happen is this particular amount of impedance will be multiplied by I1 plus I2 will be multiplied by two currents. One current is seen by the relay and one current is unseen from the relay, known as the Infeed from the remote bus. So this particular impedance as well as the fault part of the impedance will be multiplied by this current to give a voltage rise, give an additional voltage rise which will be measured by this relay. This relay will measure the voltage rise of this part. Voltage rise means this is 0 voltage. The voltage at the relaying point is VA. That will be according to this equation. It will come, see, let's move from this side. I1 plus I2 into Z12, assuming 0 fault resistance. I1 plus I2 into Z12, this impedance over this voltage rise over here, plus the voltage rise along this circuit. This is I1 into Z1L. So this will be the voltage at this relaying point. So what is the current at the relaying point? It is only I1. This relay is not able to see the current of this. The actual fault current is not seen by this relay. So what will this relay measure? This relay will measure VA divided by IA. It will measure. So this equation divided by I1 will yield Z1L plus I1 plus I2 divided by I1 means 1 plus I2 by I1 into Z2L. This particular area, this I2 by I1, this is my error. This is my extra impedance that this relay is measuring. So what will happen? Suppose a fault is at 105%, let us say. The relay will see the fault at 120%. This relay will see a higher apparent fault impedance due to this remote end infeed. So what will happen? The relay is seeing the fault at higher impedance, so it is seeing the fault further away. So I have calibrated the relay, let us say, to respond to faults up to 120%. But 120% seen from this end is being reached at 105%. So relay sees fault up to only 105% within its zone 2 reach. So what has happened is its zone 2 reach has actually decreased. It cannot see 120% anymore. It is seeing only 105%. Now come to the third statement. When the relay measures more apparent impedance than actual, then the effective operating zone of the relay decreases and the relay is said to underreach. Infeed causes underreach. This is the concept of underreach. You'll hear it here and there every time. Generally reduces the effective reach of zone 2 and zone 3. Zone 1 is not that much affected because zone 1 only the fault impedance will be able to will be affected, because the other part, this relay, this current in zone 1 fault, this relay is receiving at least this end current. It is not seeing some more impedance. Only the resistance to the fault will change due to the infeed. So, and that is why zone 2 needs to be taken at 120% to take care of all faults within 100%. We'll study zone 2 philosophy. There you'll see zone 2 philosophy is to protect the remote bus. So when we have to protect the remote bus, we cannot be satisfied with 100%. We have to take some extra impedance in our reach setting so that even for a bus fault, for a fault on the remote bus, this relay is able to see this fault over here. Otherwise, this relay will see this fault somewhere further. So it will not be able to trip for this bus fault. Okay, this is the underreach. Next concept is just the opposite, that is overreach. Overreach, when it happens, when the relay measures higher fault current than actually flowing into the fault. How it can happen? When there is a very high load at the load center. Suppose end B has a very high load. End A is the source. It doesn't have any source. All the load is being taken away over here. So what happens if we have a, let's say we have a fault at this terminal. Let's say this is a 100-kilometer line and this is also a 100-kilometer line. The impedance is 100 ohms. The impedance, this one over here, is also 100 ohms. So actually the fault occurs at 200 ohms or 200 kilometer or 200 ohms should have been seen by this particular relay. Now see what is happening. Again we come to this equation. The voltage at this point, VF, I have written, it should have been written VR. VF will be what? 100 kilometer into 200 ampere or 100 ohm into 200 ampere. The voltage is rising from here to here. So what is the voltage at this point? Assuming this point voltage is 0. It's a dead ground fault assuming. So 100 into 2000, the voltage rise at this over this line, plus 100 into 4000. This is not 2000 anymore because 2000 is being taken away from this bus. So 100 into 4000. So what will be ZF? ZF will be VF by IF. So ZF will be 100 into 2000 by 4000, means 2 by 4. And this 100 will remain as 100. So what this relay is seeing, it is seeing a total impedance of 150 ohms. So the fault which occurred at 200 ohms, the 200 ohm fault occurring at 200 kilometer distance is being seen as a 150 ohm fault, and it will be seen by this relay to be occurring at 150 kilometers. Suppose I have a zone 2, so this fault should have been originally in zone 3. Suppose I have set my zone 2 at 150 ohm as in this example. So this relay will operate for this out zone fault. Okay. So what happens is relay sees faults up to 200% within its zone to reach instead of zone 3. So a 200% fault is being seen as a 150% fault. Now let's see what has been written. Similarly, when relay measures more current than available at fault location, we have outfeed effect. When relay measures less apparent impedance than actual, then the effective operating zone of relay increases. I had set this relay to operate till 150 ohms or 150 kilometers, but this fellow is operating up to 200 kilometers. So that is called overreach. It is overacting. It is overreaching. Underreach is underacting, not acting till what I have set it to do. And this is going out of his own potential as acting more. Overreach. This is more dangerous for the protection engineer because underreach is also problematic, but overreach is more problematic because this is a totally out zone fault, but this line will excess strip. So the selectivity is being hampered to a very high extent. Excess stripping of line is taking place for a fault out zone. So how does it happen? High load current at remote bus, T point load. This is vital. T points, all those T things we take out from the we tap consumers directly from protection. I mean from transmission lines. They are susceptible to this overreach because that particular load current is not being measured by the relay during faults. That excess load current is the current is being excess measured by the relay. It is not as per the fault current. Fault current is lesser, my relay current is more. That is overreach. Okay, now we come to the distance zones. Now come to zone 1. Zone 1 is the primary protection for any fault within line section. But this but is vital. I should have underlined it. But shall in no case strip for faults beyond line section or for remote bus faults. So zone 1 is only up. Zone 1, even if it trips till 99%, it is okay, but it should not trip for remote bus fault or fault in adjacent sections. Forbidden. Zone 1 responsibility up to 80%, 85% of line. Zone 1 forbidden not to operate for faults on remote bus. Zone 2 responsibility is to cover remote bus. Okay, so this is generally instantaneous trip. Reach limited normally to 80 to 85% of protected line to cater for possible overreach. Overreach means acting more. Zone 1 acts more, I am in a very dangerous situation. Due to, why does it act more? There are a lot of errors. Transient errors in CTPT CVT. I am explaining why it is 80%, why not 95%? Because when we add up all these errors, then this around 15% errors will come adding up all these things. Transient errors in CT, PT, CVT caused by DC component of fault current, harmonics in line current, point of switching. DC component of fault current is all about point of switching of the fault. What voltage, at what voltage point the fault is taking place. Inaccuracies in line impedance data. Improper transposition causes phase-to-phase and phase-to-earth impedance to be asymmetrical across phases. Now see, generally we don't use different phase-to-phase and different phase-to-earth impedances. We correct it by K0 factor, that's a different issue. We don't use data like this. The R phase line length is, or R phase line impedance is 100 ohms, Y phase it is 90 ohms, and blue phase it is again 100 ohms. We don't do that. We use all 100 ohms for the same across all phases. My relay is not designed to act according to phase. The setting is for all phases. If you don't have proper transposition, the impedance data across phases will be different. So that is why these inaccuracies, we are very much doubtful. Okay, if I set till 95%, what is going to happen? Relay itself has more measurement errors, more so in high source impedance ratio scenarios. I have a slide on this one. high SIR scenario, something high SIR scenarios, it goes some measurement errors are more. Omission of effect of mutual coupling in parallel lines during setting calculations. Even till today, mutual coupling in parallel lines, we have mutual compensation, but those are applied only for fault location, not for zone decision. Majority relays don't apply. Only I think Siemens takes it in zone decision. Others are all in the fault location calculation. High prefault power flow angle makes the relay at sending end susceptible to reactive overreach and receiving end susceptible to reactive underreach. This one I have a slide, later on we'll try to. It's a little complicated. Okay, now about zone 2. So zone 2 has to cover this part. This is our zone 2 cover. It will cover this bus, responsibility to cover remote bus. So now zone 2, the primary protection for remaining 15 to 20% of line including remote bus must be ensured that even for highest in feed, a fault at remote bus is cleared by zone 2 at relay end. We have to ensure that even for the highest amount of in feed, the remote bus is covered. Okay. What is the reach consideration? I'm coming to this checkpoints. These are the checkpoints. Reach consideration, generally for single circuit lines, we take 120% of line section. Percentage may be set higher if in feed from adjacent lines is considerably higher. If the in feed is higher, you feel that the remote bus is a very strong bus and my relay location is a very weak bus behind, you can increase this 120%. There is no issue with it. You should increase. For double circuit lines, in order to take care of the underreach due to mutual induction, it is 150% of line section. Now, what are the checkpoints? What are the things we have to be careful about? We should not allow, suppose there is a long line followed by a short line. We have a 100-kilometer line followed by a 10-kilometer line. Let's say the 100-kilometer line has 100 ohm impedance, 10-kilometer line has a 10 ohm impedance. So the zone 2 of this is 12 ohm only, but the zone 2 of this is 120 ohm in order to, as per this philosophy. What will happen if a fault occurs over here? It is in zone 2 of this line also and zone 2 of this line also. So what will happen? For a fault on this bus, this F point, this relay will also trip and this relay will also trip. So that we cannot allow. Under such circumstances, the T2 of this particular relay should be increased. If zone 2 greater than line section plus 20% of adjacent shortest line, then zone 2 timer needs to be increased. 50% is taken just for security. It can go up to 80% because zone 1 is 80% of this line. It can increase this particular factor, but we on the safer side if zone 2 is greater than line section plus 50% of adjacent shortest line. Matlab if zone 2 overreaches this middle point, better increase the zone 2, better increase the zone 2 time by at least 150 millisecond from this particular relay, which is the short line relay. Another thing you have to be careful about is it should not encroach into the next voltage level. Generally, zone 2 doesn't encroach. That is the problem of zone 3. Encroaching of voltage level means supposing this I talked about a 10 ohm conductor, 10 kilometer line having a 10 ohm impedance. The same 10 ohm impedance can come for a 100 MV, 100 kV 50% transformer. Now 10% may be too low, but if you have 2-3 parallel transformers, then this 10% can happen. So this impedance is also 10 ohm. Okay. So if you have a fault over here, this is outside the differential zone of this, you have what will clear this fault? The backup overcurrent of this, maybe due to some reason this does not operate, HB backup overcurrent will have to clear this fault. Then it might be possible that this T2 set at 300 millisecond will trip faster than the backup of this or backup of this. We have to be careful that transformer encroachment is also not taking place. Generally, this is more dangerous. This, if it happens, you have to be careful. Rather, you decrease the zone to reach a little bit so that the other voltage level encroachment doesn't happen normally. So again, I want to tell you, setting is a art basically. It cannot quantify it in. It varies from utility to utility, person to person, ideology to ideology. So the general things are written in books, but in general, it is the practice that will help you. Learning from mistakes probably will help you. We are coming to zone 2 timing. Zone 1 timing was no matter because it was instantaneous. But zone 2 timing we have philosophies. As we have talked, it is the backup of remote bus primary protection. It is the backup of remote bus primary protection. So it is the backup. Zone 2 at this bus is the backup of zone 1 of this remote bus. So if zone 1 of this remote bus fails to operate, then we'll have a LBB. If this bus has LBB or breaker failure protection, then we'll have LBB operating over here. So we have to coordinate the zone 2 time with LBB of this bus. So what will be the time? It will be LBB operation time of this bus plus CB opening time, let us say 60 milliseconds. All this CB will open to clear this fault. LBB operate all the CB, all the breakers of the remote bus will open. So we'll have to take a 60 millisecond time for that. So 260. This zone 2, this zone 2 should not operate before LBB of the remote bus clears the fault. So we have to let this zone 2 reset along with the load current. It is having load current, so resetting will take a little time. We take 40 milliseconds for that, and we add a margin of 50 milliseconds. So 200 plus 60 plus 40 plus 50 comes to 350 milliseconds. That is the CEA recommendation is 350 milliseconds. I've written it over here in the diagram also. It is. So typically 350 is the CEA recommendation, but okay, 300 to 500 we generally keep. Some utilities keep 400, some 300 is a little on the margin. Okay, now if you do not have LBB protection in the remote bus, then you can reduce it to maybe 200 milliseconds. In case of radial lines, probably where you don't have LBB protection, then zone 2 may be coordinated with remote bus zone 1 time. If you don't have LBB, then you need to coordinate this one with this LBB. You need to coordinate this one with zone 1 of this, provided no overlapping takes place. So that is this 5th point over here. And higher time needed in case of long line followed by short line that I have already discussed. In case remote bus does not have LBB, TZ2 may be 200 meters. This is the same point. There's the diagram is this one. No remote bus LBB, TZ2 may be made 200. But normally we don't do. We keep it at 300 only. Okay, next slide. We come to zone 3. This is zone 3 protection. Now this is backup of CB of the longest line at remote bus. So any fault, this remote bus is going to have a short line, long line, medium line, all sorts of lines. The zone 3 of this relay R1 will take into account the longest line from the remote bus and promise to protect this line if the relay at the remote bus longest time does not operate. That is the philosophy of this zone 3. With maximum infeed effect. कोशिश करेगा. With maximum infeed, it will try to protect. So generally the minimum reach is 120% of line section plus longest line. Line section plus longest line. Line section plus longest line. It will take, and 120%. This factor 1.2. This 120% comes from underreaching due to remote end fault infeed. all are feeding to this fault, so it is actually increasing this fault impedance. So the relay, this R1 relay will not see the fault at over here, it will see the fault somewhere far. So then also this relay has to operate. So that factor is this one. The factor 1.2 may be increased to allow for increased Infeed. I have in the one slide, not today, in the next session, I'll show a complicated setting example where this was set to around 160, 50, 60% of this longest line, because the fault Infeed at the remote bus was so high. The maximum reach for quad characteristic, it is not a big limitation, since the load impedance applies only to the resistive reach. For the mode we have a limitation, because in the mode the resistive reach cannot be set independently. So over there, if I have a very high zone tree, then what will happen, the line might trip for normal load. So over there, the maximum zone tree limitation comes into picture, which is normally the minimum system voltage divided by 1.732 into Imax as a phase current. Imax is the 1.5 times 15-minute thermal rating would be a safe value, and minimum system voltage would be around 85 to 90%. In 220 kV system, normally 90%. In 132, it is 85%. As the operators or the utility practice, no hard and fast rule has been given for this, but the logic is it should not trip under load conditions. Under emergency load transfer conditions, zone 3 should not trip. Typically, this limitation will be there if there is no load encroachment function enabled in the relay, or the relay does not have a load encroachment function. If it has, then this also is not a limitation. Okay, we come to the zone 3. Zone 3 encroachment. This is important. Zone 3 encroachment is a very common problem in all lines. In any voltage level, we have a high problem in zone 3, because the zone 3 reach is taken quite high. So it is very obvious that the zone 3 will encroach into transformers or other, it will encroach other zone 3s. So those things we'll have to check, and if necessary, the zone 3 timing has to be increased. Okay, now here is one particular point. Let's take this example. I have a 100 kilometer line followed by a 100 kilometer line followed by a transformer with a 10 ohm impedance. Not one transformer, maybe multiple transformers working in parallel. So suppose there is a fault at the transformer LV terminals having a 4000 ampere fault current from the HV side. Suppose 1000, 2000 is being fed by these, the Infeed at this second level bus, second level tier 2 bus we call it. This is tier 0, this is tier 1, this is tier 2. 4000 ampere is the fault current, out of which 3000 is being provided by the remote bus itself. So what will, and over here, let us say we switch off this line. We switch off this fault source over here. Now, what is happening is that this particular impedance will be multiplied 4 times, because this relay is seeing 1000 ampere at the fault current, and the current over here is 4000 ampere. So the voltage seen by this relay will be 4 times because of this. So this 10 ohm will not remain 10 ohm, it will become 40 ohms for this relay. So that is what I have written, 100 plus 100 plus 40 equal to 240 ohms it is seen. So then also if this, now what is this relay set at? Let's say this relay is set at 100 plus 100 plus 100 plus 100 multiplied by 1.2. So if it is 1.2, then it is not a problem. Then it is 200 into 240, right? That is why I wrote it. So this zone 3 is set at 240 ohms, let us suppose over here. Then this will operate for this fault. Okay. This will operate. I'm repeating just once more. Yeah, I have a fault over here. This impedance 10 ohm is being helped by the Infeed over here. This impedance is increasing due to fault in feed from the remote bus terminals, but then also this relay will operate. So I need to either coordinate this time with the backup time of this. For this fault, let's say this ICT or transformer trips in 1 to 1.2 seconds. So with this 200 millisecond delay, I'll have to keep this T3, this zone 3. Then only I'll be able to be safe and sound. Okay, for this encroachment also, I don't have a problem. The thing to remember during studying encroachment is that in the remote bus, do not switch off the strongest source. See, I did not switch off the sources over here. I kept these sources. I switched off these sources. If you switch on this source, then what will happen? This current will increase so that this fault will not be seen in zone 3. But someday it might happen that the strongest source on your remote bus is off. It might happen. Or in a sequential tripping, this becomes off. Then also this zone 3 should not trip earlier than this backup protection. That is why this N- contingency, when we design zone 3 reach or zone 3 time, should be taken that the remote end most strongest fault in feed, that should be switched off and checked. You don't need to switch off all the inputs. Everything will go off and only this line will remain. Then you will never be able to set zone 3 to such a high level. Everywhere there will be encroachments. But the strongest input, it should be switched off. That will be that is a very real time what I have seen in my experience. Real time it gives good results. Most of the times it will operate okay. This fellow will not trip for remote bus transformer faults. And if it encroaches, suppose this is encroaching in spite of this N-1 contingency, then better is you increase the time over here. Otherwise, things might go wrong. Someday or the other, it will go wrong. Okay, this is about zone 3 encroachment into the next voltage level. Are cleared earlier than zone 3 operation. Zone 3 time may be increased to 1.2 to 1.5 seconds. Minimum 200 millisecond margin should be with the backup of this. Otherwise, we'll face problems. And now come to the zone 3 timing. Zone 3 is the backup. Zone 3 is the backup of remote bus backup. Zone 3 का जो timing है, that is not set with this emanating of the further bus timing. It is not. It is set with the remote bus only. But zone 2 was backup of primary protection of remote bus. Zone 3 is backup of backup protection of remote bus. What it means? Either zone 2 of remote bus, or if some line doesn't have distance protection, it is being protected only by overcurrent at fault, then backup of that backup protection. In this particular example, there is a these two lines are protected by distance zones, and this line is probably a radial line protected only by backup protection, matlab directional overcurrent at fault protection. This relay R2. So this will operate for this fault in the remote bus at 350 milliseconds. Some zone 2 may be 500 milliseconds as discussed earlier. But the highest of the backup times is this particular relay R2, which is 600 milliseconds. For a fault at remote bus over here, 600 millisecond timing will be taken for this relay to clear the fault. Zone 3 of this relay, R1 relay, will be backed up with this 600 milliseconds, not with all these. So we need quite a little high time. Normally, वो इतना calculation कोई करता नहीं है. The best possible is, see, in this particular example, 600 plus 60 will be the CD clearance time of this, 40 will be the resetting time of this, and 100 is the margin, safety margin. It's written over here. So around 800 milliseconds is coming as a zone 3 of this R1 relay. So normally we keep 800 to 1200 milliseconds is okay. Even if zone 2 is 500 milliseconds, then also we don't have a problem. if larger zone tree is used where there are several encroachments into zone tree, if larger zone tree values are used where there are several encroachments into zone tree of other lines, it is prudent to increase the zone tree timer by another 200 milliseconds. Suppose I can see the zone tree of this line is overlapping the zone tree of this line. I can see it by fault study. Then it would be prudent if we increase it a little bit, maybe 1 or 200 milliseconds more, because zone tree operation is very rare. We don't plan for zone tree operation. Okay, so rather excess operation of zone tree would be very dangerous for a lot of issues. It could create a lot of issues. And another point about zone tree reach is not about timer, is that it generally lies between the power swing block inner boundary. In Indian scenarios, it lies like that. For very long lines, it might come, the zone tree will be greater than the power swing block inner boundary can be, but normally in our case. There's another point written over here. If relay allows different timers for phase fault and earth fault loops, they can be set differently for faster tripping. Maybe I want a phase fault tripping a bit delayed than the earth fault. Earth fault I need a faster tripping. If it allows, then in zone tree you can have a different yield, because as it is zone tree timing is becoming quite high. So somebody might think, okay, itna der tak nahi rakhenge, let me trip, at least for earth faults, let me trip it a bit faster, or maybe for phase faults, I might trip it a bit faster. Typically for impedance grounded systems and all, I might have a delayed earth fault operation than phase. Then we might use different timers. Normally not used, at least in my life I have not used. Okay, now let us come to the reverse zone. The reverse zone is the distance place you can keep reverse zone. Reverse zone is useful. It satisfies the requirement for SOTF, because in SOTF protection, the lines, if the closing of the line is with a busbar sort of a fault. Suppose there is no busbar protection in this particular bus, and there is some after the that will be from this line. Anyway, for SOTF also this backup reverse zone is important. So what I need is I need to cover the local bus bar with this reverse zone protection. Normally that is the philosophy. But for directional comparison blocking or POTT scheme, it has certain implications that the relay must reach further than the zone 2 of the remote relay, because in blocking the carrier send zone is this reverse zone. So the reverse zone has to pick up properly for the carrier send to take place. So that is this picture. I have a fault in the reverse direction which is within zone 2 of this line. If I don't send carrier via this relay, this zone 2 is going to trip instantaneously. So I need my zone 4, which is the carrier sending zone, to reach further, to reach more than the zone 2 of this remote end. That is what is written over here. Okay, so that the carrier send takes place properly. It does not have any problem. So under those circumstances, zone 4 reach is made higher. The basic philosophy is 1.2, the safety factor, into the remote end zone 2 minus line impedance. So remote end zone 2, if it reaches till here, minus line impedance means this part, this impedance multiplied by a safety factor should be my zone 4 reach. Sorry, this is the zone 2 minus this line impedance. This subtraction of Z2G minus line impedance multiplied by 1.2 will be my zone 4 reach over here. Otherwise, I won't be able to send carrier under all faults. If I am not able to send carrier, this relay might overtrip unnecessarily. That is only for blocking schemes, directional comparison blocking carrier scheme. For all other schemes, it is not that problematic. The reach is generally 20-25% of line section. For longer lines, 10% will also do. For lines above 100 km, 10-15% is okay. It is also the initiation of current reversal guard timer in POTT. When we will talk about carrier protection, then we'll understand it. Generally, time delay is set beyond revert zone 2. The time delay of this zone 4 will be set beyond the time delay of this end zone 2, remote bus zone. Because for a fault in the local bus bar, the remote bus zone 2, I want to operate it faster than my local zone 4. If I have a bus bar protection, this is coordinated with the bus bar protection and LBB protection of this. This zone 2 is coordinated, we have talked about. So I will I have some case studies, of course. Okay, I'm trying to finish this one. Okay, if dedicated bus bar protection is not present, then we need to reduce the zone. Then this zone 4 can be used as a backup of bus bar protection also. Then we need to reduce the 200 to 250 milliseconds to provide local bus bar protection too. Zone 4 will operate. All the, if it is a bus fault, all these 4 lines zone 4 will operate to clear this bus fault before the other end, remote end zone 2 operates. Okay, that is the logic. Now, overlapping of zone, the concept is, I just have a diagram over here. See, if a fault occurs over here, it is in zone 1 of this zone, it is in zone 2 of G, relay at G, and in zone 3 of S. That is again shown over here. I told you in the same RX diagram, the entire grid can be plotted. The F, this is the F relay I am plotting as the origin maybe. The G relay also I can plot over here. The H relay also I can plot. The characteristics of the H relay can be plotted on the same diagram. So that is a very beneficial part of this RX plane and studying distance relay in RX plane. Everything, load, power swing, everything we can plot in the same diagram. So this is about backing up. So every zone is a backup of every zone. Zone 2 is backup of this zone 1, zone 3 is backup of this zone 1 and this zone 2. Like that. This is ERPC setting guidelines. You can find it in the ERPC site itself. This is mainly what I have talked about till now. Nothing as such is different what I have talked about. Only this zone 4 you see 10% for long lines, 20% for short lines for less than 100 km. And this zone 4, if utility uses carrier blocking scheme, then zone 4 is maybe increased as per requirement. It should cover the LBB of local bus bar and should be coordinated with zone 2 of other lines. In case of carrier blocking, zone 4 can be increased as per requirement. For other cases, whatever is written over here is true. Okay. We go to the one important thing, the effect of pre-fault loading on distance protection. What happens is, this is a little complicated. We have EA and EB. We understood Infeed. We understood Infeed, that Infeed changes the apparent distance, apparent reach of the relay and increases the fault resistance seen by the relay. This is a zone 1 fault, line section fault. So the voltage read by this relay will be IA into Z1 in this Z and IA plus IB into RF. So the fault resistance is being multiplied due to the Infeed. Now what happens is that, so we would expect that the this is the RF. Actually, this is ZL. This is the line impedance over here. Then this is the resistance to the fault. Now this IB, if it is in cophasal with IA, then we have this fault resistance increasing in a horizontal direction. So that suppose the fault is in zone 2 from this particular end. So that a zone 2 fault remains, it will go straight. If zone 2 fault remains in zone 2. But if IB is lagging IA, IA is leading IB, this is in a lagging mode. Then what will happen? This fault point comes downwards, and it might be so for these borderline faults. It will encroach into your zone 1. That is called transient overreach or reactive overreach. As if the resistance is having a reactive, the resistance, fault resistance is having a reactive component. This is this one, so it might go. Again, in the same way, if the source, the EA is the prefault load flow is from EA to EB, then this will happen. But if the prefault load flow is from EB to EA, then the opposite will happen. Then a zone 1 fault can be seen in zone 2. The phasor diagrams I'm not explaining in details. Any book you can find, or this happens. You can understand from this if you do it a little bit. Let me go a little bit faster. So the main thing is that if it's the import initially, then underreach will happen. If the load is from EB to EA, then the fault point will move upward. So a zone 1 fault can be seen in zone 2, which is underreach. If the fault point is from EA to EB, if the load is from EA to EB, bus A to bus B, prefault load, then the fault point moves downwards. Then overreach may happen. That is a problematic area for us because it is overfitting a line. The fault is in zone 2, it is being seen in zone 1. You have to generally for 5 to 10 degree downward tilt is the safe for majority scenario. What is downward tilt? I have in the next slide. You have to do load flow studies in general to determine the maximum load angle for the difficult situation. For places where there is a very high power transfer, for long lines with bulk power transfer capability, 5 to 10 degree may be chosen by default so that this overreach does not happen. This is what we are more concerned about. Okay, next slide. This is example of 3-4 relays, which is this is the tilt angle I was talking about. This is a G21G characteristic. You can have it straight, but you also have a non-homogeneous angle. This happens actually due to non-homogeneity of the network. One side is advanced in phase. One side voltage is more advanced in phase than the other side voltage. If the sending end phase voltage is advanced than receiving end phase voltage, then the fault point will go down. So I need to choose my homogeneous angle as negative over here so that the reach looks like this and not straight. This is typically for ground faults mainly. Okay, in Siemens, this is a Siemens relay characteristic. The reach, they have this alpha angle, which is a tilt. You can use a tilt over here. This is a Areva relay. You have a tilt applicable for all zones. This is also a GE relay, tilt applicable for all zones. This one, see what these GE guys have done. They have not even given a chance for the user to change. They are giving the tilt as per the line angle. You give the line angle as 80 degree, the tilt becomes 10 degree. You cannot do anything about it. Okay, in the Outfeed they have given although this is an example just. So this is a graph which is taken from the Siemens relay manual. As the R by X increases, R by X means if you have set your resistive reach far higher than the reactive reach, then the chances of this encroachment becomes more. The tilting of the polygon is more necessary. So they have given a guideline. Okay, if this is my R by X ratio of the zone, in zone 1 X is 40, R is 40 ohm, X is 10 ohm. So R by X becomes 4. At that particular time, if the load angle is 10 degree, then choose a tilt angle of approximately 5 degree. This is the graph that describes it. Just a guideline given for line angle greater than 60. Of course, all line angles are greater than 60. Fault resistance. So this is okay. This part I did not find in much in books. Whatever I have read, this particular portion, what exactly is fault resistance? Fault resistance, we all know it's arc resistance, power footing structure, all those things. Now, exactly how it happens when a fault occurs, what are the resistances involved? That I have covered in this next 2 slides. Over here, I might be a little bit wrong. If I am wrong, please correct, because this is something that I could not find in books very well written, well documented. So let me share the next slide first, then I'll come over. So what happens is, suppose I have a arc fault. Suppose I have a arc fault over here. Suppose a tree is touching. Let us take a concrete example. That will be easier. Suppose a tree is touching a conductor. Now, how does a conductor look like? Let us see. This is a transformer, generator, equivalent, neutral. This is the source, equivalent source. All the transformers at this local bus being parallel, equivalent source. The line I am showing only one phase. The line is coming via the conductor it is going, and these are the tower structures. Okay, this is the R phase insulator. This line is the R phase insulator. Okay, so and this is the tower structure impedance. This is the tower footing impedance. Although tower structure impedance is not mentioned as such, because tower structure in nowadays all are metal towers, it does not have much impedance. Compared to the footing impedance, the structure impedance is very less. But in a wooden tower, the structure impedance becomes high. So that is why I have mentioned differently over here. The footing impedance is the portion below the ground, and the structure impedance is the portion above the ground. Till this groundware to the portion where it is buried, that turn I have taken a structure just to give a real feel of the thing. Now what happens when a tree touches a conductor? So the tree can touch directly, or in general when in a wind flow, when the tree is touching, an arc will pass from the conductor to the tree to the ground, and it will get distributed to the local end and the remote end. Let us say 10,000 ampere is the fault current, and 6,000 ampere is coming to the local end, and 4,000 ampere is going to the remote end. Remote end we are forgetting. Let us forget for now. Let us concentrate only on the local end. Whatever is happening on the local end will also happen at the remote end. The remote end relay will take care of it. The local end, what will happen? This current has to return to the base, to the source. Source does not mean one substation. Source means one substation over here, one substation over here, one substation over here. But majority of the current will return to the nearest substation. Okay, from the nearest substation. Okay, now what will happen? This 6,000 ampere will have two parts. One is directly from the fault point, it will go via the ground to the transformer or this neutral, parallel neutral, and then add up to the bus. There's another part, that is via the tower footing and the structure, it goes up to the ground wire. The maximum current will be flowing to the nearest two towers. This tower and this tower. Maybe out of the 6,000 ampere, only 1,000 ampere is flowing in this IG portion, the direct ground portion. 5,000 ampere is flowing, out of that 4,000 ampere is flowing to the first tower. The second tower is taking care of only maybe 1,000 ampere maybe. After that it dies down, it will not be that much. The nearest part it will follow. Okay, so what this 5,000 ampere is encountering on its way? The tower footing of the next tower, the structure resistance of the next tower, it is going to the ground wire. To the ground wire, assuming very less impedance of the ground wire, it is now this ground wire is again connected to the substation earth mat. Now from here it goes down and it goes to the via the substation earth mat. It goes to the transformer neutral, and all these are also connected to the substation earth mat or powerhouse earth mat, whatever, switchyard earth mat. So this is the pathway of this whole thing. Now this neutral transformer neutral, if there is only one transformer, then the whole current will come through this transformer. This is handling both these currents, IG. Now after that, this is again flowing back to the source, to this point. This is the pathway is somewhat like this. The pathway is somewhat like this. Okay, as I'm showing. So what are the impedances that we have to be careful about, which my distance relay has to incorporate? It is the arc resistance, the resistance from the conductor to the touching body. It is the touching body resistance, the tree resistance, then the tower footing resistance and the tower structure resistance. Generally these two are taken together. The tower footing resistance only we consider. structure we don't measure as such, because metal structures does not have that much resistance. So these three resistance are coming into picture most of the times. Even if there is a lightning strike in this line, then the lightning will flow over here and then probably flash over on the tower structure. A different path is followed, but again then this tower footing and these things will come into picture. Okay, now I am going back to the previous one. So over here I have a diagram of a tower body. This is the ground where these are the phase conductors. Let us take this as the tower body. This is the tower body and this is the tower footing resistance to the ground. And this is a structured resistance. You can consider this structured resistance included in the tower footing resistance also and consider this as zero resistance. No problem. Now there are two kinds of faults. First of all, let us take a LL fault, that is easier to understand. LL fault can happen when there is a flashover between two phase conductors. So what is involved? Only the resistance of the arc. The distance what is involved, DLL, is the phase to phase conductor distance that is involved. And probably the wind will carve out this arc to a little bit. So we do not take the straight line phase to phase distance. We take the maximum curvature possible, that is pi, the semi-circumferential arc of that will take place. Suppose the wind is carving this arc so much that it becomes a semicircle. That is probably the maximum thing that can happen. Worst possible scenario. So this DLL is taken as the face-to-face conductor distance, or a little bit multiplication, maybe a factor of 1, a factor of 2 will, some pi by 2 will come into this picture, so that it is the worst possible case. That is the distance of arc in a face-to-face case. There is a very remote chance. Okay, during insulation flashover, this fault resistance will be the arc length for a LL fault. I am talking about in this portion, not in the LG one. So the RF will be R arc of R arc face to face, which is denoted by this particular resistance. See over here, R arc face to face. We can easily understand this. There can be another thing happening which creates LL fault, but the spacing is high. The tight string faults between face to face. That is not a arc, that is maybe arc is. There might also possible that flying, something flying, and remember in lightning during a storm, one of our tin shades flew and settled over a conductor. So that is an object creating a fault. A tin shed from somewhere over the powerhouse got flown away during the storm and got set. So this is that I have denoted by R tree phase, tree, as if a tree is falling between two conductors. So this resistance will be much higher than the arc resistance. So it is not that face-to-face faults should only incorporate arc resistances only. There is a possibility that it might have to encounter higher resistances. So it's better to use a little bit more. Do not only wait for, or do not only take arc resistance as the only resistance parameter for face-to-face faults. Okay, so this is what is given in these two paragraphs. Coming to the LG faults. LG faults are a little bit more complicated. LG fault, there can be tree touching, as I had explained earlier. Then what will happen? There will be three impedances involved. R arc probably, maybe. R tower will be there, structure will be there, and the R tree resistance will be there. Generally, these dry tree resistances are quite high. 30 ohm, 40 ohm has also been seen. Okay, there have been faults, LG faults, where the flashover has taken place between the conductor and the river structure. The conductor has come down so much during sag, maybe the flashover had took place between water and river. So there is not tree, but anyway, what I mean is the arc resistance and arc length and all don't be guided by this length I have shown, the creepage length and this length over here. The resistances may be quite high. But anyway, if we take into consideration that tree resistance, most of the things will be covered. There should not be much, nothing more. Normally 20-30 ohm tree resistance if we consider, your distance protection will pick up for most impedance, most resistance faults also. Okay, so the tree touches, so these three will be the resistances. Now, if there is an insulator flashover, which is the form of this lightning strike. What happens in a lightning strike is that lightning strike falls on the ground wire, but the ground wire is connected to the tower body. The tower body becomes the lightning voltage. Now there is a chance that huge voltage, the tower body gets lifted up to that particular voltage, and there is a conductor over here. So there is a chance of flashover via the insulation, probably if it is raining or it is the insulation is dirty and all, which happens in most of the times. So there's a flashover through this creepage distance, or there might be a arc is flowing. Both distances are given the same, not that this will be same exactly, but the idea is that, so there this arc face to ground will come into picture, and there the distance of the tower with the single conductor will come into picture with a curve, with what I told, the wind might curve this arc a little bit. Okay, arc PG, then what will happen? This lightning will flow to the ground maybe, so involving the tower footing resistance and the structure resistance. This lightning strike has to get grounded, so the distance will have to take into account these three impedances. So on a overall, the tower foot in a LG fault, the arc resistance and the tower footing resistance are coming into picture, as well as the object resistance if it is a fault through the object. And for a LL fault, the arc resistance is the primary contributor, but the object resistance can come very rarely. Okay, I'm not sure if I could explain this one very properly. I tried my best. If you have questions, I will obviously answer later on. Now let me cover this one. Now there's a concept called resistive reach. Now resistive reach is very easy, but you need to understand one thing: LG loop and LL loop. There's a term called loop resistance and phase resistance. Now in quad characteristics, what is possible is to set the RNX separately. You all know that. So ground distance should always be quad to incorporate larger fault resistances, because this tree and all is not going to generally fly about the air and create face-to-face faults. Trees will remain on ground and create ground faults, so higher resistance invariably occurs for ground faults. So the ground distance should be always quad. More ground distances आज का दिन नहीं चलता है. With the advent of numerical technology, we do not use more relays, at least for the ground distance. We always use quad because it can help in taking higher resistance values, so that all faults, even high resistive faults, can come in the distant zones. We do not have to wait for the directional arc fault to operate for high resistance faults. Of course, we have it as a backup. Fine. If we have a 100 ohm fault, then no distance relay is going to pick up. There are faults in this world. I remember a fault in a Brazil river. It was a 500 ohm impedance fault, and they had a hell of time with it. Some case study I remember just. So resistance is not that it is only 30 ohm, 40 ohm, 50 ohm. It can be very high. In the rocky sides, the resistance, the tower footing and all resistances are very high. काफी high. So there the resistance which has to be more. Okay. Now this is a diagram from the ABB REL 670 relay. This is a loop thing. Loop thing means the current starts from here, the fault resistance and the current will return to the source. So this return part is the return. Return means this one. Again taking you back to the earlier slide. The return is this one. It's IGW, IG, all this. This is the return. This part, no, this part, the resistance impedance encountered by these currents is taken care by the K0 factor or the K0 expansion of the distance relay reach. The other part, these are these physical resistances that this current is encountering, that the distance, the setting engineer has to take it into account. These parts, these unknown impedances will be taken care by the K0 factor in the ground fault scenario. The physical impedances, physical resistances has to be taken care by the setting person. That is why we need to set the R thing like that. Okay. Now, see, this is a phase 2 arc fault loop in L1. We have the line resistance also, but remember, line resistance is taken care by the tilt of the polygon. Line resistance does not mean the fault resistance. Fault resistance is the arc and tower footing resistance, which in ABB RL670 relay is mentioned very well by this parameter RFPE, resistance to fault for phase 2 arc loop. That is the meaning of this word, acronym. And in a phase to phase, what happens? You have RFPP and we take only arc resistance over there. RFPP means resistance to fault in a phase to phase loop. And in a 3-phase fault, the loop resistance is like this. Every relay in its manual will give you the loop diagram. What is the fault loop and the definition of the resistance, reactance and fault resistance it is following. So that manual you have to see and understand which parameter to set what. Matlab, we will not set arc resistance and tower footing resistance in R1. We will set line resistance in R1. The line also has resistance. That is also to be seen. We will set arc and tower footing resistance in RFP. And maybe the tree resistance over here also. Okay, this is what I mean over here. This one, LG loop should provide maximum coverage considering fault resistance plus arc resistance plus tower footing resistance. LL loop, fault resistance plus arc resistance only, as I have discussed earlier. Reach should be set to provide coverage against all types of anticipated LL faults subject to check-off possibility against load point encroachment. In LL loop, load encroachment causes a problem. So we'll have to set the line-to-line resistive reach a little bit carefully because maybe load encroachment can happen. That we have separate slides on how to calculate the load encroachment and all that. Effect of Infeed. Now, this is another important area. This is important. We calculate the arc resistance by this Van Warrington formula, where L is the, we all know it, the production engineers know it. L is the arc length in meters, I forgot to write, and IF is the, this is multiplied, no, this is equal to. This is the arc length in meters, which is equal to the maximum face-to-face conductor spacing in meters. What I explained, face-to-face fault takes place when a conductor and another conductor, there's an arc in between. There's some arc flowing between, so that is the length. This length is talking about the face-to-face length, the face-to-face distance between the conductors, or the arc length. Generally, we don't take the face-to-face directly length. We increase it by a little bit factor so that we can take care of the wind curvature. The wind curves the arc, thereby increasing the resistance of the arc. That is why it is taken. And remember one thing very much. This is vital. This IF is the minimum ampere fault current, not the maximum. When the current decreases, the arc resistance increases. So in case of decreased fault current also, you need to calculate the arc resistance in such a manner that even for the lowest fault current, the fault comes within the distance relay resistive reach. So this is minimum fault impedance. An example I have just given over here. Let us say in a point TV system, the LL separation is 8 meter. Assume minimum fault current is 1000 ampere. The calculated arc will be 28707 multiplied by 8 meters divided by 1000 to the power 1.4, which comes to around 14.49. Approximately the RSPP, as explained in the previous slide, the resistance to fault in a phase-to-phase loop will be 15 ohms. Tower footing resistance to be measured by utilities and then decision taken. Hilly areas have higher values, 40, 50, even I've heard from Power Grid that in Binaguri and those areas the resistance is above 50. They have such a troublesome time in controlling that fault resistance. They are paralleling and paralleling and paralleling, so that tower footing resistance decreases. A very typical value would be no. Therefore, for a arc fault, the fault resistance, tower footing plus arc will be equal to RFPE equal to 25 ohm for the lowest zone. Now, what I mean by lowest zone, this is what I wanted to tell you. When the fault takes place within line section, only two currents are involved, I1 and the remote bus current. The real fault, my end fault current, my relay fault current, the fault currents in by the relay and the remote bus fault current. But if the fault takes place in zone 2 section, the next fault section, then the remote bus fault current is also coming into picture. This line now, ground line now. The remote bus fault current is also coming into picture, and the remote bus is also coming into picture. So the fault resistance gets multiplied by I1 plus I2 plus I3 instead of I1 plus I2 over here, which has the effect of increasing the fault resistance by this factor I3 by I1. So in a section fault, the increment of fault resistance is relatively lesser than in a second zone fault. Again, in a third zone fault, if the fault is in the third zone, then the infeed effect is much more. You have I2 coming from here, you have I3 coming from here, you have I4 coming from here. So all these four currents are being multiplied by this fault resistance. Okay, this relay is seeing I1 plus I2 plus I3, but this relay, the zone 3 of this relay is not seeing all these four fault currents, it is seeing only I1. So suppose there is a 10 ohm impedance to the fault, it will reach this fellow as 40 ohm impedance, 40 ohm resistance. The real fault resistance is 10 ohm. If I consider I1 equal to I2 equal to I3 equal to I4 equal to 10, equal, all equal. Let us say all are equal. I1 equal to I2 equal to I3 equal to I4. Then this 10 ohm impedance will become 40 ohm over here. So what is the meaning of these words? Meaning is that for a zone 2, you generally should multiply this particular, this is just this. When you are doing a zone 1 resistance, you are setting the zone 1 resistance, better multiply this RFPP into 2 times lagbhag, depending on the I2 by I1 ratio or the I2 contribution. Assuming equal contribution, you have to, you cannot sit back and take only 15 ohm. You have to take it 30 ohm. You have to increase this by a factor 2 because of this effect of this fault current. And for a zone 2 fault, maybe increase it by 3 times. This 15 ohm has to be increased by 3 times, so that this relay is able to capture this fault properly. Otherwise, it will see it in much farther. It will underreach. Due to resistance, it will underreach only. So the resistive reach, we are talking about only resistive reach now, not underreach, overreach. In the resistive angle, and the R axis, the fault point is moving, not on the X axis. Okay. Now, for a zone 3, maybe it has been increased further. So typical RFPP for zone 1 will be, let's say, 30 ohm. For zone 2 will be, let's say, 45 ohm, 50 ohm maybe, multiplying by this. And for zone 3 it may be up to 70, something around, let's say 4 times of 60 ohm, 4 times of this. So 30, 45, 60 would have to be set for this relay to capture all these 3 faults within their resistive reach. So every zone, if you set as 15 ohm, it won't be able to capture. Similarly for the earth fault scenario. In earth fault, you multiply 25 by this Infeed factor and then take a decision. But again, this is not a hard and fast rule. It has to be seen. You have a very short line, you have a very high fault resistance. The R by X is becoming very higher. There you have to reduce. You cannot go for such high fault resistance. So you have to have compromises over here. Okay, setting resistive reach. Okay, let me complete this and then I'll move to 1 or 2 case studies. Because otherwise it will be boring probably. I'm not sure how boring I am. Okay. Okay. Resistive reach setting. See, this is what I have written over here. RG1 is 2 into 25 equal to 50. RG2 is 4 into 25 equal to 100 maybe. Maybe 4 times you increase this 25 ohm which we calculated for one particular the resistance that we calculated. But if I have to capture this fault, I have to take into account the remote end Infeed multiplying this fault resistance. Then all I'll be able to do. And RG3 such and such. For the reverse zone also you need to multiply because generally bus faults have a very high fault Infeed. The current seen by the relay, the line relay is about 5 times lesser than the currents in a bus fault. Because all the other sources are contributing to the bus fault. For a resistive phase to phase also these factors remain and it will get multiplied. Limitation in shorter lines, what I was talking about. Generally some limitations are imposed by relay manufacturers regarding R by X ratio in zone. Typically, I remember in RL 670 manual, the RFP is less than 4.5 x1. It should be less than 4.5 x1. Matlab x1 is 1 ohm, RFP cannot be more than 4.5. x1 is 3 ohm, 1 ohm, RFPP should not be more than 3 ohm. Because otherwise, this chance of reactive overreach, what I was talking about in that slide I covered, if R is far less than X, the tilt angle has to be there. Otherwise, we'll face problems. Okay, option 1, option 2. The slide is about options, about how to set the resistive reach. Option 1 is to use the progressive Infeed factor and multiply the resistance to fault by the Infeed factor to arrive at the resistive reaches. Option 2 is delimited by late encroachment for all zones and it takes all zones will have same reach, and that I'll calculate not on the basis of all these things, I'll calculate on the basis of load. Of course, whatever we calculate, the minimum value is the arc resistance and the arc plus outputting resistance for this. For this it is the arc resistance, for RFP it is the arc plus outputting. That is the minimum, you cannot go below that. For the maximum part, they can do like this. Okay, I don't need so much calculation, Infeed and all those things. My problem is my limitation in the top part, in the higher part is load. Load में trip नहीं करना चाहिए. So there, the RFPP can be set at 60%. The phase-to-phase resistive reach can be set at 60% of the minimum load impedance. It should have been load resistance, not in Z. It should have been R. So mistake over here. And the RFP should have been set at 0.8 load minimum. Okay, load means resistive load. Option 3 is the lower portion. Option 3 generally we don't use because otherwise higher fault resistance faults won't be captured. If you use only RR and RR plus CFR outputting, then all faults you won't be able to capture. that I've seen from my personal experience, I can see. Okay, this is the load encroachment characteristics as seen in the relay. So what this load encroachment characteristic does is that you can increase your zone 3 resistive reach as much as you want without having the limitation of load tripping in real-time load. Because when a fault occurs, it will occur somewhere over here in the on this line, and the movement will be somewhere on in the horizontal. So there the reach is higher. On the resistive line, the reach is lower. So I can get the advantage of both. I can get the advantage of higher fault resistance coverage, as well as my line will not trip on load. I can carry emergency load on the line. I can use it for heavily loaded lines. And load encroachment function should be used for long and heavily loaded lines. Otherwise, over there the zone 3 is quite high, the Infeed factor is quite high, so you have to set the resistive reach a little bit more to catch the high resistance points. And generally, the minimum load resistance is 1 into 15-minute thermal rating of the line, or the associated bay equipment minimum rating. Suppose I have a CT which is 800 ampere. My line is very powerful. So my CT can burst if I allow it for 15 minutes to take. So the lowest equipment rating is the one which decides the thermal, ultimately decides the thermal rating of the line. And the voltage, depending on the voltage level, 0.85 to 0.9 is the normal. And power factor 0.30 degree is okay. Normally in transmission lines, power factor of 30 degree is not crossed. It is never more than that. Okay, now I will not cover this. I am going into this. I am not covering. I'll cover in the next one. Okay. Now I'm going into 1 or 2 case studies so that it becomes a little bit interesting. Hope it was interesting. I don't know. So this is about. Okay, let me cover this. This case study is about a portion which I have not taken. This is a case study where there was a fault in this particular bus and the relay trips from this bus. There was no tripping over here. There is no tripping over here. So why? First of all, the no tripping problem over here should not be taken into account because there was no relay over here as such, or the relay over here, both the lines were faulty. Leave it out. The relay over here was okay. It was a numerical relay, so there should not be any problem. The problem in this relay was that the overcurrent starter was set at such a value. The overcurrent starter was set at such a value that the distance relay did not even start. We have a portion called starters, overcurrent starter, under impedance starter, overvoltage starter, undervoltage starters. So that I've left out. So what happened was that overcurrent starters did not start, and then this one tripped. Ultimately, because of overcurrent non-start of distance protection over here, because the overcurrent starters did not start, and that it should have fallen in between the zone of this. I mean, zone 3 of this. The fault fell in between within zone 3 of this particular bus, the Gola 132 kW. You can see the fault was within the reach, but the starter current value was set at such a high value that it did not understand the fault. So it tripped from backward. This is the main learning from this. Now why it happened? Sometimes the ratio was 200 by 1 or 200 by 5. After the CT ratio was, so then the overcurrent starter was maybe set at 1 I nominal. After the CT ratio was changed to 800 by 5, then also it remained same at 0.1 I nominal. So now the overcurrent starter became 800 ampere, and on this particular day of fault, the strongest source behind was off. So the fault current did not rise to 800 amperes for these two relays. But this particular relay, being a 442 P442 MICOM relay, this relay overcurrent starter is default at I think 10%. 10% is the overcurrent starter value. There's a delta starting and all those things. Those were also there in the coverage. I'll cover next because I won't be able to finish within 1 p.m. Okay. So when we change CT ratios, if there are overcurrent and these starters, the starter reaches have also to be changed. Otherwise, fault may start ही नहीं लेगा. Okay, that was a lesson learned from this particular thing. There was one more lesson learned. I have not mentioned it over here because that is a typical case study. This line also the zone tree picked up, but during a fault transition, R phase CT bus converted into RY fault. The distance of the 442 P442 relay dropped off. During a fault loop transition, P442 relay distance function dropped off and started retiming itself. That is why overcurrent tripped. Otherwise, this was a tree fault from this also. This line is very long, 86 kilometers. So zone 3 of this is 86 plus 25 into 1.2 minimum. So that covers this bus. Because this is too long, this particular fault was covered in this bus and there was no impede over here. So this relay was covering this fault. But due to fault loop transition in Areva relay, this relay did not trip to distance protection. If I get a chance to take class on only case studies, then I will take up this case study. Took around 5-6 days of investigation to understand why this relay also saw a fault in probably zone 3. This relay saw a fault in zone 3 but did not trip in zone 3. What is going wrong? Relay is okay, relay is healthy. So if I get a chance, I will share the DR and make this fault more lively one. Over here, I just wanted to say that when you change CT ratio and things like that, change everything related to that CT ratio. Do not change only the distance zone and leave the starter current at the original level so that the relay does not start even. Okay, now I come to another. Oh, I have it over here. I have it. So I am not explaining the whole thing. See over here. All distance timer also drop off during the fault loop change. This one. But the overcurrent I1 greater than start is continuing. That is why it is tripping in overcurrent. At 550 millisecond almost, just before the lapse of zone 3 time, the distance zone dropped off. The thing dropped off due to a fault loop change. This I am talking about this relay, this Chandiland relay, which tripped. The correct tripping occurred at this relay. But this did not trip in the distance protection. It tripped in overcurrent protection. The explanation I am giving over here. And it was tested at laboratory, similar effect found. Any loop change from LG to LL to LLL, distance primer was starting afresh in Areva relay. Same thing found in ABB relay too. Siemens I have not, I've forgotten Siemens. Probably I'll do and let you know. This I have written. P442 has fixed thresholds. 2 consecutive data samples lies above V, delta V greater than 0.1, 10% voltage change and 20% current change for fault detection. Both fulfilled by Chandiland relay, but the previous substation relay, this thing was not fulfilled because it was a different relay with a different overcurrent pickup. It did not have this voltage and delta I sort of pickup. It had a normal overcurrent pickup. Unless the fault current crosses 800 amperes primary ion pickup. That was the previous one, which did not trip. So this is the important new information that got. These relays do not think that a fault started in A and if it goes to AB, then again the timer starts. There are settings in the relay which can control this thing. In Siemens relay we have settings where there is a chance of Siemens has cell has FEL311CRC. In a loop change, the timer will not retime. The timer will continue. that is settable in these relays. In Areva, I never found any setting. It is not settable, but in a loop change, the timer will re-continue or something like that. So this was one case study. This is a CT sorting error. I was talking about the CT error, what to say, CT star point not towards line. In this particular case, there was a fault in this line. In this bus, all zone 4 starts were taking place, but no zone 4 trip. Fine, sorry, no zone 1 trip over here. No zone 1 start, zone 1 trip. All the 4 relays were taking zone 4 start, and all tripping occurred from zone, remote zone. Zone 3 over here. This is a longer line, zone 3 probably. This is a shorter line, zone 2. This one was zone 1, only one was zone 1. So since this one was zone 1, we thought that the fault will be in this line. So this relay should have malfunctioned. We checked the CT polarity and found that the CT polarity was reversed. But before we checked the CT polarity, what we did was we performed a bus current balance. What is a bus current balance? We go to this substation or call this substation up and tell them what is your bus power being shown by the different, I think SCADA or something like that. Not SCADA, I've forgotten, 2015 SCADA, whatever. But what we did was we summed up the megawatts of the bus. So the active power has to balance in a bus, otherwise it won't work. Reactive power can be either. Active power has to balance. What was found was that all the powers were export powers, or matlab this is now one thing we know by virtue of our experience is that this particular bus is always providing power to this particular bus, because there's a generator connected over here. So always the power flow is from this PHS, Panchet Hydel we call it, to the Ramkanali bus, to this this bus. So power flow is from this bus to this bus, negative is okay. From this bus also there is a very strong bus. This bus also power flow will be normally from this line to this line. I mean from the CTPSN to Ramkanali, and this also negative power is okay because it's all import. Power flowing out is positive. So this is load, except very good. This has to be import. There's nothing about it. It has to be import. Matlab it has to be going import. This one I think will be plus. I think written it wrong probably. Anyway, the main thing was that this was also minus. How can this be minus? If all these three are correct, then this has to be wrong. Or otherwise this is correct and all these three are wrong, or some other combination. Now you see, if you add up 18 plus 18, 36 plus 10 is 46. 46 is equal to 43 plus 3. So this has to be wrong. Something is wrong with this. So after doing this from remote, we went over there and checked the power data from all the lines and then checked the CT polarity and found it reversed. What was happening? This line saw the fault in reverse correctly because the CT was reversed. These lines saw the fault in reverse because it is correct, the CT is forward. These lines tripped okay, this line tripped okay, because this line did not trip, that means the other end has to clear the fault. See how this zone 1 did not clear, and the backup I was talking, zone 2 is clearing the fault. This one is a longer line, the infeed from this line is more. So see, this fault is occurring in zone 3, not in zone 2. Although, as far as I remember, the zone 2 should cover this fault. The zone 2 of this relay should cover this fault, but because the infeed is more from this impedance is getting multiplied, so the relay does not see the fault over here, this particular relay. This relay sees the fault a little bit more, but still within its zone 2. But since the infeed, this is a 14 kilometer line, the infeed from here, the fault currents were passing through these lines. The fault currents fed by these lines are more. So this is multiplying this part of the impedance, and then it is coming through this And you can also see in this particular case under normal load flow conditions also this is a very lowly loaded line. So the fault current contribution from this would have been a bit lesser. So the multiplication which is taking place of this amount of impedance will affect this one more. That is why this, see, in a real life example, this is coming in zone 3. Okay, I think this is a very good example to show that overreach and this thing. It should have been zone 2, but it is underreaching and the fault is going into zone 3. Okay, so this is how we understood. Let